Okay, well, good morning. Like I said, today is going to be the last of the Zoom lectures. Next week, we're going to be meeting live. And we talked about this last week about starting maybe a few minutes later to allow you guys the time to actually get to campus. For those of you who are not familiar with campus, and some of you haven't been on campus, this week I'm teaching live all week to some of my classes, and I have several students who had never actually been to campus before, even though they've been at Mesa, because everything had been online. So I know Tuesday is going to be rough, right? You have to get in your car and drive, and and you can't wear your pajamas. Really, they'd really rather you not. But I would allow myself even a few more minutes on Tuesday if you're not familiar with the campus, because you may not know where you're going to park yet. The one thing that I can guarantee you, though, is there will be plenty of parking. You do not need a parking permit. This semester, again, you do not need a parking permit, but you have to park in student parking. If you park in faculty parking, you will still get a ticket because you don't have a permit. If I park in faculty parking without a permit, I get a ticket. So allow yourself a few extra minutes, and then we're in the math building, room 209. It's a computer lab. So again, once you get to campus, you'll have a routine, and that will be really, really easy from that point on. And I will send out an email reminder over the weekend that we're going to start at 7:30. I don't see any reason to move that later. And I mean, again, if it was really a major deal, in a few weeks when we go to daylight savings, it's going to be a rougher week than next week, because it means getting up an hour earlier, but we'll get used to it. Okay, that's not even a thing. Now, on the last couple quizzes, we've had some issues with some of the calculations, because I think there's a little bit of misconception on some of the things, mean, median, and mode in general. Now, remember, the calculation for mean is you add up all of the scores and you divide by the number of scores. But some of us are making mistakes because we're not taking into account if a score is repeated. If a score is repeated, you add up that score over and over and over and over again. Okay, so if I have, let's say I have the score of 10 occur 20 times, I can go 10 plus 10 plus 10 plus 10 plus 10, or I can just say 10 times 20. It's a little bit easier if I do it that way. But I have to add up every single score because there has to be exactly this many scores. And in some cases, like on the previous quiz, we didn't take into account if a score happened over and over and over again. A lot of times we only counted it one time. That will always give me an incorrect value. The median is the middlemost score. So that means you have to know exactly how many scores you have and figure out where the middle is. Remember, we did this in class when we first defined this. If there are an odd number of scores, then there is exactly one score in the middle. If there's an even number of scores, then there are two scores in the middle, okay? And I just take halfway between them. So if I've got the numbers 1, 3, 7, 11, 15, there is a middle, okay? If I throw one more number at you, let's say 16, now there's two numbers in the middle. So in this case, what would my median be? Anybody? 7 and 11 are my middlemost scores. So what's my median?
9.
9. That's it. If you're doing more than that, then you're kind of missing the point. But I had a simple set of numbers that I could easily see. What if I give you 1,000 numbers? Well, then it's the number between the 500 and 501st number. Got to go to the middle. So that's why I have to count how many. So on the previous quiz, which I don't have exactly, give me 1 second. Let me bring that up. I have it here somewhere. Now, let me go through that one. On the previous quiz, I gave you 250 students took a 10-point quiz. Okay. To find the mean, I got 250 scores. The score of 10 occurred 24 times. So I got to go 10 plus 10 plus 10 plus 10 plus 9 plus 9 plus 9, or I can say, 10 times 24, 9 times 37, and so on. Most of you did a good job with that, and you double checked your calculator. So most people gave me the correct answer for the mean. You got to use a calculator. The median is where we had trouble because there's 250 scores. If I rank them from top on down, here. By the way, you can go bottom up or top down. It doesn't make any difference. So if I'm ranking them, then I got a 10, a 10, dot, 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 then a 9, a 9, dot, dot, dot. It's looking like that. If I go all the way down the line, including the 0. Okay. How do I figure out the median? Well, I have an even number of scores. I have 250 scores. So I have to find the 125th score. And somewhere in the middle here, I have 125 scores on this side, and I should have 125 scores on this side. Well, how in the world am I going to know? You just count the frequencies. Okay, so I'll write it down. The number 10 happened 24 times. The number 9 happened 37 times. The number 8 happened 64 times. The number 7 happened 38 times. Well, right now, if I count that, 24 plus 37 plus 64 is exactly 125. That means from 7 all the way down to 0, I also have 125 scores. That's it. I just counted it using the frequencies that are given. The 125th highest score is still an 8. The 126th highest score is therefore a 7. That's how I determine my median. It's between 7 and 8. So that's why it was 7.5. Oh. Now, which is the easiest of all values? The mode. There's no calculation. There's not even counting. For the mode, I just say which one had the highest frequency. That one occurred the most often. That's why my mode was 8. My mode is not 64. 64 isn't a score. 64 is the frequency. It's how many times it happened. So it's kind of like what number got the most votes. So in an election, we don't say, 6,473,000 votes wins. No, what candidate got that many votes? We don't, the frequency isn't the winner. The frequency tells me what number is the winner. So that, now, the median for some reason gave people the most trouble on this one because we weren't taking into account, it's got to be the middlemost outcome, not the middlemost possible score, but the middlemost score that actually occurred. And if I had a ridiculous group, think of it this way. I've got 340 million Americans. And what if I have a database that has everybody's income? Well, that would be outrageous. No, that's called the IRS. The IRS has a database that has every single American's income from 2021. That's how it works, because your employer turned it in with your W-2s and things. So there's a database. Now, a lot of these people didn't work, okay, but let's take the 340 million Americans and let's rank them from the highest income down to 0. I would like to find the median income in the United States. So the computer that's already got all the numbers ranked is just going to take half of all the numbers and then go to that income right there. And that's going to be the median. It's right in the middle. You don't have to sit there and count by hand because, well, we have 340 million data points. But the beautiful thing is to put them highest to lowest or lowest to highest with a computer is trivial. I do this all the time when I'm doing stuff on my computer and I'm doing maybe my own taxes and stuff and I'm entering dates. I just go over to sort and click sort and then everything's automatically sorted. I don't have to worry about it. If I'm doing a class roster and I'm just entering all the names and I want it alphabetized, I just go to my computer and go sort, and then everything's alphabetized. That's not something that's ever an issue. So when I gave you these numbers, I gave you highest to lowest. They weren't completely random. Now on quiz 4 that you just did, I did the same thing. I gave you the numbers lowest to highest. It wouldn't have changed anything, but it's just easier to look at. So like I was saying before class, I have 3, 4, 6, 9, 10, 13, 16, 18, 22, 24. That's 10 values. I'm going to add them up. I'm going to divide by 10. That's it. That's the mean. There were no repeated values. Okay, but there was only 10 numbers. Now, when I want the sum of the squared scores, then I say 3 squared plus 4 squared plus 6 squared plus 9 squared and so on. Now, why would I ever do that? Well, because that shows up in the calculation for variance. Now, variance, the definition of variance for the sample is every score minus the mean squared over n minus 1. This is the definition, but that's really taxing. That takes a long time to do, to enter each score, subtract the mean, square it, add them up. I showed you in class, there's an easier way to do that. It's a shortcut. And it looks like this. The sum of the squared scores minus n times the square of the mean, n minus 1. This is exactly what you would actually do in a computer. This is what your calculator is actually doing. The calculator is not doing this. It's doing this. This is way faster.
I had a question about that. So that would be true if it was a sample, right? But
yes.
If it was a population, because on the quiz, it didn't specify anything. It was just
It's
a random
always,
set of
by
numbers.
the way, it's always a sample unless you know that it's a population. It's never a population, because a population would mean, I said, for example, I said, use the following values. That means those are all the values on planet Earth that could occur. No, it's always a sample unless you're told.
Because I took it as it was a population of all the scores you gave us, because there was really no description and I hadn't known that.
Yeah, no, just for future reference, because I have mentioned this a few times, it's always a sample unless you know the population, which, by the way, I said before, is very rare. The example I gave is billionaires in California. Pretty small population, right? So what's the only difference, by the way, if this were a population? What's the only difference? You would use the entire n. That's the only difference. You'd still do the formula part. The numerator would still be exactly the same. So is there ever a time we're going to have a whole population? Yeah, we might, but probably not. In real life, it's extremely rare. Now, census data, like I said, IRS, that would be the whole population. But boy, that's, we don't have access to that sort of information. Yes, Robert, you have a question?
I had a good question, Professor, because I remember you speaking about it in the last lecture about the for when we're doing our work, when we have to divide, we have to take away one of the numbers, correct? Like if there's 10 of them, we use 10, we use 9, right?
Exactly. Okay. Now, one of the things I would recommend all of you do when you're doing your work is always show all the numbers. When you're saying, here's my calculation, put the numbers down, because we sometimes miss a button on the calculator. It's possible that you did everything correctly and you have a wrong final answer because you just hit the wrong button. You didn't use parentheses or something. Always show what you did to get the answer. So that way, if you do make a mistake, it's very clear, what your intent was. So for example, on problem 3 on this quiz where I asked you to find the variance, well, first of all, like Robert said, my denominator should be a 9. Now, if you put a 10, you're going to get a different answer, but it's not going to be radically different. But again, it's not going to be exactly the same. But my numerator, the sum of the squared scores was this. I have 10 scores, and the mean, I believe, was 12.5. Now, if I took every score, and I want to make sure everybody understands, if I did it this way, which is absolutely correct, it would look something like this. I have 3 minus 12.5, and I'm going to square it, plus 4 minus 12.5, and I'm going to square it. I'm going to do this all the way down to the last score, 24 minus 12.5, and I'm going to square it. This value here, this is the formal definition, okay? Score minus mean, and now square it, add them all up, divide by 9. That's the definition of variance. This calculation, it's a long time. This is the exact same value. I thought it's the shortcut. If I just said 3 squared plus 4 squared, all the way down to the end, and then plug them in, a small percent, maybe 1/4 as many moves, and an easier calculation. Both calculations yield the same value. Okay. I'm a fan of doing it this way because I'm lazy. This just takes a lot of button clicking. that's the only thing. Now, something that requires practice, and I think some of us maybe are not getting enough practice. Remember, there's 2 sources. I said there's the OpenStax practice problems. It's free. That's the book you can go online, and then there's the Friola, which some of you said you acquired that one. But you got to practice to make sure you've got these down because the problems aren't hard. Now, starting next week, we will be in a classroom, but we're going to be in a computer lab, which is going to feel kind of awkward for a lot of reasons. I don't like lecturing in computer labs because there's a computer screen right in front of you. And so people are doing this during the lecture, so looking to the side of the computer screen. Part of the benefit of having that is I'm going to put a whole bunch of stuff on Canvas for us to practice. So when we come to the computer lab, you're going to log on, go to Canvas, and we're going to have practice stuff right there on your screen. You don't have to print stuff out ahead of time. You don't actually have to have a textbook in front of you. The stuff we're going to practice, you'll have on the screen. That's kind of a benefit. And I'll say, okay, I'd like you guys work together maybe on this problem and see if you can hash it out. We could try that over Zoom. Has anybody been in a class where you did breakout rooms, by the way, over Zoom? Anybody? Do you know what I'm talking about?
Yes.
By the way, I've been teaching over Zoom a year before anybody in the district was teaching on Zoom, because the karate school that I teach at for the last almost 40 years, we went to Zoom as soon as the pandemic hit. So out of my house, we were teaching up to 6-7 karate classes a week. I teach a weapons class. My kids are all trained and people would come over. But I'm teaching karate over Zoom. It's really difficult to teach any athletic movement over Zoom, but we did it. And what we would do a lot of times when we wanted to break out into small groups, we'd go to breakout rooms. And we use breakout rooms all the time. It's okay for conversation. I don't think it's particularly good for trying to do math, because you're in a room with other people now. It's still the same problem. You're not together and only one person can talk at a time, and it is what it is. It's not the best thing, but it's better than nothing, I guess. So when we're in class, I actually will encourage you guys to work together. I'm not going to force you to work. I know we've all been in classes where you're forced to do group work and you don't want to. But in this case, you really do want to, because if you don't know, maybe the person you're working with knows. If you do know, maybe the person you're working with doesn't know, and you can help them in their understanding. It's, to me, when you're working together, it's a win-win. Okay? If you don't know, you can learn it. And if you do know, you can help, which means you reinforce it yourself, and it's always a good thing. Okay, so the numbers, we want to get it right. Now, today is the end of the material. Today's all probability. Today is the end of the material that is on the first exam. I posted a practice test with a key. It's probably a good idea to take a look at that maybe over the weekend. We haven't finished. Friday is going to be our big review day. So Friday is the day that we're going to actually, for the first time, do a Zoom review. That was always our intent, because the exam, I believe, will be a week from next Tuesday. So Friday, we're going to Zoom review. So we'll come back to this. The reason we're doing that is I'm not going to make anybody go to campus to review. I mean, I have no problem. I live 3 miles from campus. That's not a big deal for me, but some of you, it would be far more of an effort to go to campus just for the review. So we can do the review over Zoom. Right now, I think we agreed on noon to 2. I'm going to pick your brains next week. If you guys would rather do it at a different time, we'll figure it out. I want a time that maximizes the number of people that could actually do it. That's important. So I don't want it to be at one person's convenience. I want it to be a time where you say, yeah, I can do that. I'm not at work, or I don't have another class. You don't have to come to a review. It would be very wise to come to a review, because the exam is going to look like the practice test. And you want to make sure that you can do every question. All right. So,
Professor, I had a question, sir. I'm not sure if you talked about it or not, but I'm assuming for the big exam or test, we're not going to be able to have any notes with us, are we?
Certain things you will be able to, and we'll discuss that. This class has a lot of formulas. I put a formula sheet. Somebody was asking me, are we ever going to have formulas? Like, if you go to Canvas, you see syllabus and schedule and Zoom links on the notes, and you see something that says formulas. Every formula we're going to do in this class is on there. Most of the formulas on that sheet we haven't got to. So if you look at that sheet, it's maybe kind of scary, but maybe first page of the sheet. So I will allow you to bring something like that. Now, a lot of students say, well, can I just go ahead and write my own formulas down? Sure. What's the danger if we write down our own formulas? Anybody?
It could be not the same as the one that's.
I might miswrite it. If I've already got them printed, sure, you can rewrite it in your own handwriting. That's fine. But the problem with writing your own formulas is, what if you make a mistake in writing the formula? Yikes. That's the only thing. I don't care. No work for me if you want to write down your formulas. If I've already got them printed, you might want to just go ahead and use that. But yes, This is not a class where you memorize large volumes of formulas. It's not memorizing the formulas. It's knowing which formula you're supposed to use, knowing how to correctly use that formula. That's way more important. Everybody will have access to the formulas at all times. So that you're off the hook from memorizing formulas. You also have to know which one you're supposed to use at the appropriate time. That's a good question. Now we're going to go over two very important types of probability. So I'm going to give you a scenario. Okay, we're going to go back to the dice roll problem because this is the great setup for me. On the exam, I will actually include this, by the way. I always include the dice roll chart on an exam. I think I actually put it on the quiz too, so you don't have to write it down every time you use it. It's just quick reference, that's all. Okay, so if I asked you, I'm going to roll the dice one time. 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, and we'll finish off here. You know, for those Monopoly players and you like to gamble, dice rolling is important to understand the very basics. If I said, I'm going to roll the dice, okay, I'm going to roll the dice. I would like the probability that my sum is, let's say, 7. What is the probability? Now, we did this last day. So remember, probability is how many ways can your outcome occur? And what is the total possible number of outcomes? So let's start with the total possible number of outcomes. Now, we actually made a table last day. Total number of outcomes is 36. Okay. How many of those are 7? Anybody? How many of the outcomes add up to 7?
6.
6. So if I said, what's the probability you roll a 7, a total of 7, you'd say it's 6 out of 36. That's it. That's not complicated. It's really a count more than a calculation. Now, here's the thing. I'm rolling the dice. I get totally distracted. Okay. Now, I'm going to tell you what happens in a moment. I'm going to ask you a different question now. Now I'd like to know what's the probability that your outcome, I'll call it X, is greater than or equal to 7. That means what's the probability your outcome is a 7 or an 8 or a 9 or a 10 or an 11 or a 12? Ooh, I have a whole bunch of possible outcomes now. Okay, everybody with me? I want to know, so maybe you're playing Monopoly. You know, if I roll anything bigger than 7, then I'm going to land on Boardwalk and Place or something. You're playing a game with dice, and maybe rolling 7 or more is good, maybe rolling 7 or more is bad, but you'd like to know, what is the likelihood I roll 7 or more? So now, do you remember if you have your table, the probability of 7 was 6 out of 36, plus the probability of 8, that was 5 out of 36, the probability of 9, the probability of 10, the probability of 11, and the probability of 12. This came from the dice roll chart we set up last day. Okay, so all I have to do is add those up. So if I said you're going to roll the dice one time, what is the probability your total is at least 7? That means 7 or 8, 9 or 10 or 11 or 12. I add them up. 6 plus 5, that's 11, plus 4, that's 15, plus 3, that's 18, plus 2, that's 20, plus 1, that's 21. Okay, does everyone agree? 21 out of 36 is the probability? That's more than half, right? So I'm more than 50% likely to roll 7 or more. Cool. I can reduce that. That's always a good idea. Great. Here's the thing. I know that if I roll the dice, the probability that my sum is at least a 7 is 21 out of 36. Great. Here's what's happening. I'm asking you that question, and while I'm talking to you, I'm not paying attention, and one of the dice flies out of my hand. I'm going to roll both of them. One of them flew out prematurely, and you glanced over, and you noticed the die was a 6. You weren't cheating. I dropped one of the dice prematurely, and then I'm going to let go of the other one. And maybe you're a gambler, maybe you're a betting person, but the question was, what's the probability my sum is at least a 7? And you said it's 21 out of 36. What if you saw one of the dice landed a 6? Does that change your answer? if you saw one of the dice landed a 6, now what's the probability my sum is going to be at least 7? Think about that. You know one of the dice is a 6. So if one of the dice is a 6, then doesn't that make these my only possible outcome? You saw, I mean, you were reading, you saw one of the dice is a 6. I call it insider information, on stock trading. You have some information that other people didn't know. I want to know what's the probability my sum is at least a 7, but now knowing that one of the dice is a 6, aren't every one of these totals at least 7? Do you agree? If one of my dice is a 6, then the other die is a 1, 2, 3, 4, 5, or a 6, but no matter what, all of my totals are at least 7. So this is the probability that I roll a sum that's at least 7. But if you knew one of the dice was 6, now isn't it absolutely certain my sum is at least 7? In other words, won't the probability now be 1? Ooh. Now think about that for a moment. If I have some information, it can change my probability. That's exactly what we're talking about here. If I have information, now, I'm not talking about impossible rolls of the dice. We're just going to take the rolls of the dice that exist. But if I know something about one of the dice, it could change my outcome. Here's the reason. If you knew one of the dice was a 6, your sample space is no longer all of the rolls. Your sample space would only be the rolls that have a 6 in them, because you know one of the dice is a 6. Let me ask you a similar. And we're defining a particular type of problem that's really, really important. It's something we do in real life. And for those of you who are sports fans, I don't know if you guys pay much attention, but I love it in the NFL. They're always throwing probabilities at us. They say, we're getting ready, and it'll say the probability of your team winning if they score the next point will be this. If they don't, it'll be this. If the probability of them making the playoffs if they win will be this. Do all of these probabilities before a game starts. What they're giving you is what is called conditional probability. And this is actually a thing. I can calculate the probability of many things fairly simply because I can see what the outcomes are. I can see the sample space. It's not really that complicated most of the time. Conditional probability says, will the probability change if you know something about this? I'm going to give you a simple example. I'm a big sports fan. I'm a Lakers guy. So if I said, what's the probability the Lakers win tonight's game? And, they'll use this for betting, in Las Vegas, everywhere else. But what if I knew that LeBron James was not going to play tonight? Do you think that would change the probability of the Lakers winning? Anybody? If LeBron James was not going to play?
Yes.
Of
He's the
course.
GOAT.
It would
He's
probably
too
have would you say it might have a huge impact?
Yeah, I would, because he's that good.
So if I said, what's the probability of the Lakers win tonight? And you say, okay, the probability is 0.6. That's what, the odds are. That's what the thing line is. Probability is 0.6. Oh, but wait a minute. What if LeBron doesn't play? Maybe the probability drops to 0.1. So saying, here's the probability, and here's the probability of this insider information. That's what I'm talking about. That's why, again, I'm not a gambler. I don't condemn gamblers, but I'm not a gambler. I'm not. It's never been my thing. I love the mathematics. So what you do is if you're a gambler, you pay attention. Hopefully you read things, I'm going to bet on this football game. Oh, I just found, Tom Brady is not playing today. He's injured. Something like that have a huge effect. That's what we call conditional probability. The probability of something occurring, the probability of something occurring when I know this other thing. Oh, knowing the other thing can affect the probability. You guys just said, if the Lakers' probability of winning is number, the probability of winning if LeBron doesn't play is probably a much lower number. So that's why conditional probability I have to take into account. So we're going to show you how to actually calculate that. We're going to look at it. Going back to this example here, I'm going to do a similar problem. Okay, I'm going to do the same thing. I'm going to roll the dice one time. So I want to find the probability, the sum is at most, let's say at most 6, knowing one of the dice is a 3. So now the question is, what's the probability the sum is at most 6? That means it's 6 or 5, 4, 3, or 2. That would be all the rolls up here. 6 or 5 or 4 or 3 or 2. It's not a lot of rolls. But I have insider information. I know one of the dice landed a 3. Does that affect my probability? Yes, it does affect. In other words, this is no longer a possible outcome. This is not a possible outcome. One of the dice was a 3. So what are my possible outcomes? My possible outcomes would now be all the rolls where one of the dice is a 3. So I'm going to write like this. I'm going to circle every roll where at least one of the dice is a 3. What that means is my denominator is no longer 36. My denominator is now limited to the rolls where one of the dice is a 3. If I know one of the dice is a 3, then 5, 5 can't be an outcome. Now, how many outcomes do I have possible? Well, if I count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now my denominator is 11, not 36. Oh, what's my numerator? Well, look at all of the outcomes here where the sum is at most 6. That would be 6 or less. 1, 2, 3, 4, 5. These 5 outcomes. So this is my answer. I said, you know, one of the dice landed a 3, the probability is 5 out of 11, which is very different than if I didn't have any insider information. So I'm going to show you the formula. It's actually a formula, and it's actually simple to work with. Okay, so here's what happens. You have 2 events. And again, I'm going to leave that up for a moment. I have 2 things going on at one time. I have A and I have B. Okay, I have events A and B. Now, A might be that I roll the dice. B might be that I flip a coin. A might be that I had for breakfast. B might be that I'm going to work. I just have 2 different things going on at the same time. And I'm able to calculate the probabilities. So here's how conditional probability works. I'm going to show you the notation. So we want the probability of event A occurring given we know B occurs. That's my insider information. If I said, what's the probability of event A? It might be a coin flip. It might be a dice roll. It might be pick a card, any card. It might be I'm counting how many people run the red light at an intersection. What's the probability of this thing happening? It's something that I can calculate. Now, what is the probability of that thing happening given that I know this other thing happened? So we write it this way. It's the probability of A vertical bar B. This is the notation. This is the probability of A occurring given we know B occurred. This is universal statistics notation. This is not a quotient. Vertical bar means given. What's the probability of A given we know B has occurred? First thing is, if I know B has occurred, that limits my sample space. Limits my sample space to only the outcomes in B. So my denominator right off the bat will be the probability of B, which is not, by the way, that's not intuitively obvious, but that's what it is. My numerator will be all of the things where A and B both occurred at the same time. That would be the probability of the intersection. And this, we'll do several examples. This is the formula, conditional probability. The key is remembering that when I tell you, given that something has occurred, given that you know you rolled a 3, that changed my sample space to all of the outcomes that had a 3 in them. Okay, that's why that's the new denominator. It's not the old sample space. It's much, much, much smaller probably. So we'll do some of these, and I'm going to give you some pictures to make it really clear. Some Venn diagrams where I can actually look and count, calculate. Okay. Erase this. My eraser is dying on me. A different one.
Yes, sir, I have a question before we move
Yep.
on. I'm just making sure I interpret it correctly. So whenever you give us a question where an event is given, that's the formula we use. So you mentioned with the formulas,
Yeah.
not having to memorize the formula, but knowing which formula applies to what type of question. So if the question, in the question it says something is given, then we automatically use that.
Yes, and a lot of times, by the way, a lot of times it's not even really a formula. I don't want to say common sense. I hate using that in mathematics. Let's keep it really simple. Okay, let's do something like a coin. I'm going to flip a coin. We did this already. I'm going to flip a coin 3 times. And we said last time our sample space was head, 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 tails. Head, tails, heads, heads, tails, tails. Make sure I'm not getting the glare here. Tails, heads, heads, tails, heads, tails, 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 heads, tails, tails, tails. That's my sample space. Okay. I'm going to ask you a probability question. Well, right now, you all know that every denominator is going to be 8 because there's 8 possible outcomes. Agreed? So if I said, what is the probability that I get exactly 3 tails? 1/8. What's the probability I get exactly no tails? 1/8. What's the probability I get exactly 1 tail? 1, 2, 3. 3/8. We know this. We've done this. Okay. Those are all fairly simple questions. Now, without helping the think calculator, I'm going to flip a coin 3 times. What's the probability I get 3 tails? And you're going 1/8. Oh, wait a minute. What's the probability I get 3 tails knowing the first 2 flips were also already tails? What's the probability I get 3 consecutive tails if I tell you my first 2 flips were already tails?
That'd be like an 80% chance, wouldn't it?
Think about how many times do you have to flip the coin if you already know the first 2 are tails?
1 time.
What's the probability on 1 flip that it's a tails? Heads or tails? What's the probability of a tails if I'm only flipping it 1 time?
50-50.
50%.
So 1/2. Now, does everybody agree that if I flip it 1 time, the probability is 1/2? Okay. Here's where conditional probability is really useful. Don't think formula. Don't think formula. Think it's right there in front of me. I'm going to flip a coin 3 times. You know the probability of 3 straight tails is only 1 out of 8. What if I said I've already flipped 2 tails? I only have to flip it 1 more time. What's the probability of 3 tails? You'd say 1/2 because I only got to flip it 1 more time. Let me make it even easier. What's the probability that I get 3 consecutive tails knowing my first 2 flips were heads? Anybody want to tackle that one? What's the probability that all 3 of my flips are tails, given that you know the first 2 flips were heads?
And we're still trying to get tails, you said?
What's the probability that all 3 flips are tails if you know my first 2 flips were heads? Is it possible to have 3 tails if the first 2 flips were heads?
No, that's impossible.
So the probability would be 0. Because if my first 2 flips were heads, it doesn't matter what my 3rd flip is. Like I can't have 3 tails if my first 2 were heads. Oh, so here's what I'm saying. Have insider information. So I'm flipping a coin and you already know what my first 2 outcomes were. So what's the probability? What's the probability I get at least 1 tail if you already know my first 2 flips were tails? You already know my first 2 flips were heads. Or you see, if I already know something, maybe then you're only thinking about 1 flip. The insider information is what I'm talking about. So I'm going to use a really simple example here again. What's the probability that I get exactly, let's keep it simple. What's the probability I get exactly 2 tails? I'm going to flip the coin 3 times. Probability I get exactly 2 tails. I have 1, 2, 3 ways that could happen. So if I'm going to flip a coin 3 times, the probability I get exactly 2 tails would be 3 out of 8. We all agree with that. Okay, now, what's the probability I get exactly 2 tails if you know one of my first 2 flips was a tail? What's the probability I get exactly 2 on my 3 flips if you know that one of my first 2 flips was the tail? Oh boy, think about that one. You
Wouldn't that also
know,
be 50-50?
yes, because I only got to flip it one more time. I only got to get one more tail. Do you agree with that? Okay, so do one more. I want to flip the coin 3 times, and what's the probability that I get exactly 2 tails? You know my first 2 flips were tails. I'll flip it one more time.
50-50.
It's still 50-50 because I have to flip the heads now, don't I? So would you say that knowing the information might actually make the calculation easier sometimes, if I already know? Now, I'm going to give you another simple one. I do this stuff in even my higher level classes because sometimes everybody wants to use a formula and sometimes they don't want to just think the obvious. So here's the deal. Let's say you are all part of a club. You're part of a club at Mesa College. It's a big club. Let's say, we'll keep it really simple. There's 100 people in your club. There's 100 students. Okay. Let's say in your club, there are 60 women and 40 men. I want to make it so it's not the same number. Okay. We want to elect the president of the club, a president. And we're going to make it really simple. We're not going to have a popularity contest. We're just going to write everybody's name on a piece of paper. We're going to stick them into a hat. And then we're going to draw a name out, and that person gets to be president of the club. By the way, the president has to do all the work, has to prepare all the food, has to clean up later. Maybe you don't want to be president. I don't know. What is the probability of any individual therefore becoming president? Okay, one name. Anybody tell me what's the probability that any individual will become president? 100 students. I'm going to draw a name out of the hat.
One over 100.
1 over 100. Yeah, piece of cake. 1 over 100. Now, here's what you didn't know. Administration says, no, I need the president to be a woman. I need the president to be a woman. This year's club, the last 5 years, it's been a guy. So we want the president this year to be a woman. So is it still 1 out of 100? You know, administration says, no, it has to be a woman. Then what's, now, let me make it simpler. Let's say, Rosalind, you are one of the people that are in this club, so your name is in the hat. Is it still 1 out of 100 that you'll be selected? Knowing that only a woman can be selected, what's the probability? Before, Rosalind had a 1 in 100. But if you know I'm going to select a woman, then what's the probability that Rosalind will be selected? Anybody?
160.
1 out of 60, because there's 60 women. Oh, now Salvador wants to be in the club. If you know I'm going to choose a woman, what's the probability that Salvador will be selected? Knowing we're going to choose a woman, what's the probability that Salvador will be selected? He's one of the 100 names in the hat. Knowing we're going to choose a woman, what's the probability of Salvador being selected?
0.
0. Does that make sense? This is why insider information. Did that require a formula for you to answer those questions that I just asked you here? Did that require a formula? No, that was just right in front of me. There's 100 people, their names went into a hat. If I know only a woman could be selected, and there's not 100 in my denominator, there's 60. That's what the conditional probability says. My sample space changed. If I know a woman has to be selected, my denominator can only be 60 because there's 60 women. Oh, now the probability if you're a woman of being selected would come to 1/60th. If you were a male, your probability would be 0 because only the women's names are getting selected from the hat. So that's what conditional probability is. Now, let me do it from a Venn diagram point of view. Sometimes it can be easier to see that way. All right. So say we want to break down San Diegans into the following group. Okay. Let's say there's two types of people in San Diego. All right. Let's say in group A, you have a car. In group B, let's say have a dog. Okay. Now, does everybody in San Diego have both a car and a dog? What do you think? Does everybody in San Diego have both a car and a dog?
No.
No.
There are people in San Diego that have neither. You don't have a car or a dog.
Yes.
I have a 17-year-old son. We don't have a dog. He doesn't have a car. There are people that don't have either. So everybody in San Diego will fall into, here's the car people, here's the dog people. These are people that have both. Out here are the people that have neither. Everybody okay with that? So let me give you some numbers. Let's say in San Diego, I'm just going to make it up. Let's say in San Diego, 70% of the people have a car. Let's say in San Diego, keep it simple, dog. I don't know, let's say 40% of the people in San Diego have a dog. And let's say in San Diego, 20% of the people have both. Okay? Making it up. All right, so let's start off by filling in the numbers. Remember, I said always start with the intersection and then work your way out. So being in the intersection would be 0.2. Now, A is the car people. I've already got 20% of the car people here, so how many should go here? How many are car, no dog? This is 70% of San Diego. How many are car and no dog?
20%.
Well, no, 20% would be the both.
Oh, I'm sorry. I'm sorry.
Car and no dog would be here.
0.5.
0.5, because that's got to add up to 70%. Okay. Now, on the other side, 20% of the people are in both. How many are dog, no car?
0.2.
0.2. That's got to add up to 0.4. If I've done this, then I'm doing a good job. So therefore, how many are the neither? I didn't tell you, but you can figure it out. How many are in the neither group?
0.1.
How did you come up with 0.1?
It adds up to be a whole.
It's got to add up to 1. Perfect. When I add up all my probabilities that are possible, they got to add up to 1. There's 0.1. So that would mean that 10% of San Diegans have neither a dog nor a car. Okay. Now, if I asked you, I'm going to select a San Diegan at random. At random. What is the probability a San Diegan selected at random has a car? You'd say it's 0.7. Agreed? I'm going to select a San Diegan at random. What's the probability they own a dog? You'd say 0.4. It's easy. I'm going to select somebody at random. That's the probability because that's how many San Diegans have a dog. Okay. But what if we change the condition now? Whoops. I'm sorry. See, sorry. A and B. Sorry, not C and D. I forgot what I wrote down. Now, here's the thing. I'm going to go to all the dog people in San Diego. And I'm going to say, what's the probability that you own a car given you own a dog? I'm only going to ask the dog owner now. I've changed it. I'm giving you insider information. I'm not going to all San Diegans. I'm going to only the people in this block here. I'm going to the dog owners. What is the probability that you own a car given you own a dog? Now, remember what the formula said? The formula was the probability of A and B, that's the intersection, over the probability of B. Okay. If I use that formula, what's my numerator? Wouldn't it be 0.2? You with me? What's my denominator? 0.4? What's 0.2 over 0.4? You can use a calculator or you just tell me. 0.2 over 0.4. Nobody?
It's still technically 1/2, right?
It's 1/2, 4 point, you can go 0.5 or 1/2. Now, 40% of people in San Diego own a dog. 60% of the people, or 70% of the people own a car. Okay. I said, what's the probability you own a car when you're a dog owner? If you're a dog owner, could you have possibly come from this group here? No. You have come from this group here. No, you had to come from this circle right here if you're a dog owner. That's what this circle represents. Oh, so look at this circle. These are car owners here. These are non-car owners. I said, what's the probability you own a car when you come from this circle? Look at circle B. Isn't exactly half of circle B here? Half of circle B is right here. What was your answer? Given that you're a dog owner, the probability you owned a car was exactly 1/2. It's interesting, isn't it? Maybe that wasn't obvious. That's what conditional probability is. It was exactly the same. Excuse me, it's only this. Now, let me change the question. Now I'm going to go to car owners. Okay, I'm going to ask the people that own a car, what's the probability you have a dog given that you own a car? Well, the formula is still, it's probability of the intersection, but now it's over probability of A. Here's why. Different question. I'm only looking at the car owners, so I'm only looking at the people in this circle. What is the probability you own a dog if you're in this circle? Well, those are the dog owners. Okay. If you're in the circle, 0.7, 0.2. Why? The probability of the intersection is on top. The probability of A is on the bottom because my sample space now only includes car owners. I'm only considering the people that own a car. It's not all of the people. So this answer, we can just write 2/7. That's not a happy decimal. Let's write 2/7. Now, question. In this example here, is the probability of owning a car the same as the probability of owning a car given that you own a dog? No. Is the probability of owning a dog, this number, the same as the probability of owning a dog given that you own a car? No. Conditional probability was different. Okay, most of the time the conditional probability will not be the same. Now I'm gonna ask you a question. All right, you're gonna play poker today and you're a gambler. We can calculate the probability that you're going to win. We can calculate that. So I'd like to know, once we calculate the probability you're going to win, what will be the probability you're going to win given your next door neighbor had eggs yesterday? Do you think your next door neighbor having eggs yesterday will have an effect in your probability of winning? Probably not. Meaning that the probability of you winning and the probability of you winning knowing this insider information is probably exactly the same thing. That's really important. That doesn't always happen. I'm going to give that a name. And I'm going to change this scenario just a moment too, by the way. Let me go and do that. Yeah. This is a general. This is not about cars and dogs. This is just in general. The probability of A given B occurred is equal to just simply the probability of A. Meaning knowing B occurred did not actually change my probability. You do not have control over that. You're just reading the numbers. You don't actually try to make an interpretation. You do this calculation, you do this calculation. If they turn out to be exactly the same, then that means that knowing B occurred had no effect whatsoever. Then we say A and B, and the word is, are independent. They are independent events. If the probabilities are not equal, we use a different word. Anybody want to guess what word we'd use? There's only one other word. It's, if these are the same, they're independent. If they're not the same, then they are What do you think? Anybody? Take a cut. If probabilities are not equal, then they are
Dependent.
dependent. That means one is dependent on the other one. So you agree that the probability of B given A was not equal to the probability of B, and probability of A given B was not equal to the probability of A. That means they were dependent. That means knowing you had a dog changed the probability. Knowing you had a car changed the probability. If the insider information, if knowing something happened changes the probability, then those things are dependent on each other. If knowing something happened did not change the probability, independent. It's kind of like one cannot affect the other. So let me give you a different picture to illustrate something like that. Okay. New problem. It doesn't even matter now. I'll just say probability of A and B. We don't even have to have specifics. In this case here, the probability of A, let's say, is 0.8. The probability of B is 0.6. The probability of both of them at the same time, let's say, is 0.48. Okay, now I want to put in the numbers. I did a research poll. Maybe 80% of the people in San Diego like sunny days. And 60% of people in San Diego like swimming in a lake. 48% of the people in San Diego like doing both. Okay, have fun with that. So 0.48 is going to go right here. How much is here? You're in A, but not in B. What's left for right here? Anybody?
0.32.
Good. 0.32, because it's got to add up. Now, what's over here?
0.12.
0.12. And if I add all that up, let's see, that'd be 89, that'd be 0.08 out here. Okay. I may or may not need this. I always like filling in all the numbers. So here's my question to you. I would like you to tell me the probability of A given B. I would like to tell you to tell me the probability of B given A. And lastly, are events A and B independent? Now, you cannot answer the last question yet. You actually have to find these values first. Okay. Now remember how it works? What goes on the bottom? The probability of A given B occurred means I'm only looking at the outcomes in this circle. So what goes on the bottom here would be 0.6. All right, like that. Over here, the probability of B given A has occurred means I'm only looking at this circle. So that denominator would be 0.8. I'm going to put them 0 because this number is 2 decimals. It's easier to conceptualize. Now, what goes in the numerator? In both cases, it's the probability of the intersection, which we said was 0.48. Okay, now get out your calculators, please. 0.48 divided by 0.6. 0.48 divided by 0.60. I mean, you can do that without a calculator, great, but use your calculator. What is that exactly?
.8.
That's exactly 0.8. Okay, 0.48 divided by 0.80.
.6.
0.6. Okay, that's not a hard calculation, but you probably want to use your calculator. All right, so when I'm looking at all of the people in this group here, okay, given that I'm in group A, 60% of them were still in the intersection. Okay, over here, when I looked at all the people in group B, 80% of them were still in here. That's what that says. By the way, isn't 0.8 equal to the probability of A occurring? That was given. And isn't 0.6 equal to the probability of B occurring? Now, my last question, By the way, you did the calculations. These were not complicated calculations. You took the given values and you wrote the quotient, you calculated. Life is good. My last question, are the events A and B independent? The probability of A knowing B occurred is equal to the probability of A. The probability of B knowing A occurred is still equal to the probability of B. So in simple English, knowing B occurred did not affect that probability. Knowing A occurred did not affect that probability. Yes or no? Are they independent? Yes or no?
Yes, they're independent.
That's the definition of independent. The probability with the insider information was exactly the same as the probability without knowing anything. That means they're independent. In simple English, event B did not affect the probability of A, because if event B affected the probability of A, then these numbers would not have been the same. But the fact that they were means, oh, okay. And by the way, it's actually the intersection. If I change the intersection, the answer would be no. Okay. Everybody, does that make sense? Okay. Oh, Rosie, you got to get it. Okay. So this is conditional probability. It's not complicated. All you need to know is which one is the given. You've got to make sure. See, these, do you all realize these are not the same question? What's the probability of A knowing this occurred is not the same as the probability of B knowing A occurred. This is its own thing, and that goes in the denominator. That guy goes in the denominator. That guy goes in the denominator. So the order is actually very, very important. So when asked, what's the probability of something happening? You always have enough information to calculate that. What's the probability of something happening knowing this other thing? That makes it conditional. And so that's a little more complicated. It's not very complicated, but there's more, a little bit more that goes into that. Okay. We're going to take a short break because that's the first thing we're doing today. We have another huge thing, not complicated, but everything involves a calculator. We're going to be doing stuff that you can't do without a calculator. And it's not complicated. And it's actually some of the stuff we're coming up with is kind of cool. And some of you gamblers, this might actually help you. Not that I'm wanting you to gamble or anything. All right, let's take a short break. Let me pause the recording. Okay, now we're going to look at a different type of situation here. I'm going to introduce a word to you. It's a very mathematical word. Complement. Now, complement does not mean, oh my, you look really nice today, or that dinner was wonderful, and that's spelled with an I. Complement is a mathematical word. It's a logic word. It literally means everything else. Okay, so the complement of any group of things would be everything else that you're not including. So for example, if we were talking about a classroom and I chose one particular row in the classroom and I'd say, what's the complement of that row? You'd say everyone else in the classroom who's not in that row. In high school geometry, we talk about angles, and the complement of an angle is an angle where they add up to 90 degrees. It's sort of like the rest of the degrees I need to make a right angle. Okay, it's a common term. But in mathematics, complement sometimes makes it easier. Now, you'd say, why would I want to make things complicated? If I ask to count the particular number of occurrences of something, how many ways can this thing occur? Sometimes counting the complement can actually be easier. Okay, I'm going to give you a simple example. I'm going to roll the dice. Okay, I want you to roll the dice. Okay, I want the sum at least 3. Oops, at least 3. Now, with the dice rolls, the sum could be 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10 or 11 or 12. And we have a big table. I want the sum to be at least a 3. Well, at least a 3, what's the only roll I'm leaving out then? At least a 3 isn't the only roll that I'm not considering a roll where the sum is 2. There's only one way I can get a 2. So how many ways can I get a 3? Anybody want to guess? How many ways can I get a sum of 3 or more if I roll the dice one time?
35 over 36.
No, just the number, 35. Now, did you sit there and count? Okay, there's 2 ways to get a 3. There's 3 ways to get a 4. There's 4 ways to get a 5. Did you count all the way down to 12? Or did you use the fact that there's only one way to get a 2?
Yeah.
That's kind of the oh duh. I want it to be an oh duh. Wait, if I roll the dice, my outcomes are between 2 and my sums are between 2 and 12. There's only one way to roll a total of 2. That means there's 35 ways of rolling something bigger than 2, 3 or more. What you did was you counted the complement. You see, you without even realizing it, you automatically said, well, there's only one way to do that thing, so that must mean there's 35 ways to do the rest of the stuff. You didn't count and add up to get 35. You counted 1 and then you subtracted it from the whole. That's the key. This is what makes complements particularly valuable. If the complement is smaller than what I'm asked to do, then do the complement and subtract it from the whole. So when I say what's the probability, you correctly said 35 out of 36, which is essentially saying 1 minus 1 over 36. So if I draw a picture, okay, actually, I'm not even going to do circles. I'm going to make it easier than that. I'm going to make it easier. Okay. I'm just going to do, I have 2 possibilities. I have A and I have everything else. We'll call it B. Okay. A union B is everything. And remember, everything we usually call sample space, big S. A intersect B, there's no overlap here. There's 2 complete, we can make it simple. The A is the males in the class, B are the females in the class. A is the people that are 21 and over, B is the people that are under 21. Okay, you could break it up any way you want, but this is everybody. A intersect would be, and we usually use this symbol here, that's called the empty set. There's nothing in it. It's empty. A and B make up the whole, but they have nothing in common. And that's really, really simple to do in general. That's kind of, you've heard the old expression, there's only 2 kinds of people in this world. Okay, there's Robert and there's everybody else. That's actually a correct statement. And Robert does not belong to the group of everyone else, and no one in the everyone else is Robert, but together they make up all people and there's no overlap. I mean, you can have fun with that. There's exactly 2 things. In this case here, we would say that A and B are complements. So the definition of the complement is something and its complement together make up the whole, but they have no overlap. They have nothing in common. So in this picture, the probability of A plus the probability of B must be what? Anybody? What must that add up to in my picture here? Everything's either in A or it's in B. I don't know if you guys, that's B. I don't know if you guys can see that. I'll move the B over further. There we go. So I see it's in the glare. What's the probability of A plus the probability of B?
1.
1, because it's everything. Yeah. What's the probability of the intersection of A and B, by the way? If the
0.
intersection is the empty set, there's nothing in the intersection, then what's the probability of the intersection?
0.
0. And these are the 2 key components that make something a complement. From a mathematical standpoint, again, together they make up the whole, but they have nothing in common. So the notation that we often use, sort of the universal notation, is we say we have for event A, the complement of A, we usually use A with a little c. It's not an exponent, it just means A complement. Some textbooks, by the way, will put a bar over the A. So there's different notation universally. But the C is probably the most common. It's just easy. I have A complement. So in this picture here, the second set is A complement because B represented everything else. So going back to this statement right here. Now this is key. I want to calculate the probability of A complement in general. Let me erase this. Sorry, I need space here. So if the probability of A plus the probability of A complement is always equal to 1, then that means the probability of A complement must be 1 minus the probability of A. And similarly, Similarly, the probability of A must be 1 minus the probability of A complement. That should make perfect sense. Here's why we really like complements again, and this is true at every level of math. If what you're asked to find is more work than the complement of what you're asked to find, then always find the complement and then subtract it from the whole. So if I find the complement, either way, these are both true, whichever one's easier to find. Now, sometimes the complement might be more work, so then you just do this. So the case I gave you a moment ago where I said, roll the dice, what's the probability your sum is at least 3? Well, the complement would be your sum is exactly 2. Well, that was easy. That probability was 1 out of 36, so your final answer was 1 minus 1 out of 36, as we pointed out. So finding a complement, again, is fairly simple. So I'm going to give you some examples now. We need a calculator for the next thing. All right. There's a really, really cool outcome that comes from this. All right. So let's suppose it's a particularly rainy day. You don't feel like staying indoors. So you decide to go down to one of the local casinos. Okay. And you decide you're going to get your bucket of quarters or whatever, and you sit at a slot machine. You know, one of those things where you just do this all day long. You know, you get the overdeveloped arm from pulling the slot. Now, in case you're wondering, I've never actually played a slot machine. That's not really a good use of your money, but let's suppose you want to play the slot machine. All right. So at a particular slot machine, and by the way, every slot machine that's produced, the people who make the slot machines know exactly what the probability of winning is. It's designed a certain way. So I created a slot machine that, you know, 1 out of 1,000, 1 out of 1,000,000, 1 out of 10. That's how often somebody's going to win. Now, it doesn't mean you're going to lose, win. Now, the same number of losses, then a win. No, it's completely random. It's like a coin flip. But I know if I flip a coin, it's 50% likely to land tails. I know if I roll a single die, probability is 1/6 of any outcome. Well, a slot machine, the probability of winning will be a particular value. This is actually known. It's programmed. You know, it's not random. It's not arbitrary. And since nowadays slot machines are all computers anyway, right? I've been there. You know, you play a slot machine, you don't even pull the levers anymore. You just punch in and it does it for you. So let's say at a particular slot machine, the probability of winning, let's keep it simple, let's say is 0.002. That means exactly 1 out of every 500. That's 2 1,000ths. The probability of winning at a certain slot machine is 0.002. Now, that's not a very good probability. That means on average, somebody wins every 500 times they play. Again, not very good, but you decide you're going to play a whole bunch. Okay, you're going to play a whole bunch. Now, if that's the probability of winning, okay, I'm telling you that we know this information. Can anybody here tell me therefore the probability of losing? If the probability of winning is 0.002, then what is the probability of losing each time you play? Maybe want to try that one? What do you think? This is given.
0.998.
And how did you come up with that number?
It's less than a whole.
Well, did you just do 1 minus this?
Yeah.
Yep, that's exactly correct. Because you can win, you can lose. There's not a third option. It was postponed due to rain. No, I tied. No. When I play the slot machine, I either win or I lose. If the probability of winning is this number, then the probability of losing is this number, because those are the only 2 outcomes, and that has to add to 1. It's actually that simple in real life. all the time. It's really that simple to calculate certain probabilities. If there's only two possibilities, and I know one of the probabilities, then I automatically know the other. It's 1 minus. Okay, so you're going to play the slot machine a whole bunch of times. Let's say you decide to play, you know, like I said, you had all day, it was raining, you were bored. You decided to play 1,000 times. And by the way, I have been to casinos, and 1,000 plays is not unusual. People, this is kind of funny. I've been to Vegas a lot of times when I was younger, not to gamble. I used to go there to compete in international tournaments in the 80s and 90s and early 2000s. And all the tournaments are held at casinos, and you'd be walking through the casinos. Not only would people be there all day, they'd have gigantic buckets, like those big Home Depot buckets filled with quarters, just one after another, one after all day long, and then eventually maybe refilled that bucket. So yeah, playing 1,000 times is actually not that unusual. Again, I find it kind of a waste of money. So you play, oh, I'm sorry, that's in the glare, isn't it? I mean, yeah, I can see that on my screen. You play 1,000 times. Okay. I want you to find the probability of losing 1,000 times. You're going to lose every single time. Okay, so the probability of me winning is this. What's the probability that I win 2 times? Well, it would be this times this. Now remember the multiplication principle we talked about last day. If I do something and then I do something, I multiply the probabilities. So if I said I want you to win and then win and then win and then win, you just keep multiplying this number over and over again. But I said I want you to lose followed by lose followed by lose followed by lose. Every time you play the slot machine, it starts over. When I'm flipping a coin and I flip a heads or a tails, then the next time I flip the coin, it starts over. It's a head or a tail. The coin doesn't remember what it just landed. When I roll the dice, whatever I get, I get. Now I'm going to roll them again. The dice don't remember what they landed. Okay, the slot machine isn't keeping score. It's brand new every time you start. So the probability of losing is this every time you play. Can anybody tell me how I would do this calculation? I want you to know what's the probability that you lose all 1,000 times. It's not complicated, but what do I have to do with this number?
Maybe like an exponent?
Ah, okay. So if I said, what's the probability you lose 1 time, you'd say it's this. What's the probability you lose 2 times in a row? Would you agree it's this times this? Do you agree with that?
Yes.
So 3 times this times this times this, 1,000 times this raised to what? You said an exponent raised to the?
1,000th power?
That's it. Because that means I'm going to go loss followed by loss, followed by loss, followed by loss 1,000 times. That means I'm going to multiply this number by itself 1,000 times, or raise it to the 1,000th power. That's a little more efficient. But we know that's what it means. The exponent means I'm going to multiply that number by itself exactly 1,000 times. Now get your calculator out. So 0.998, and I'm going to raise it to the 1,000th power. Now, this is a very, very long decimal. In case you're wondering, this is a 3 decimal place number multiplied by itself 1,000 times. It's actually now a 3,000 decimal place number. I don't think anybody here really needs all 3,000 decimal places. Are you with me on that one? 3,000 decimal places, probably overkill. There is actually a common way of reporting probabilities. And this is not some universal law. This is just kind of the universally accepted way of doing it in statistics. Is we generally speaking, when we're calculating probabilities like we just did here, it's 3,000 digits long. You usually write 4. Why 4? I don't know. That's just kind of the universal norm that's always been used in probability and statistics. So usually you give a 4 decimal place number. Well, because I'm rounding it, I put a little dot over that. Anybody want to tell me what number they got to 4 places? So I need you all to do this on the calculator. Anybody? So do this, and then let's see what it says on our screen. I'm hoping you all have a calculator. If you don't have a calculator, this is really hard to do by hand. Does anybody have a number?
.1350 or 51 if you round up.
Good. 5-1 is probably better because I have to round that last place. Now, okay, what does that number mean to me? That is the answer, by the way. That is absolutely correct. You're rounding it because it just keeps going for a really long time. I'm going to play the slot machine that I have very little chance of winning on, by the way. 0.002 is not really good. You know, if I were a gambling man and you said, oh, the probability that your team is going to win is 0.002, that means your team's probably going to lose. And I'm going to play 1,000 times. What's the probability I lost every time? Do you realize that's only about 13.5%? Doesn't that mean that I might win? If it's only 13% that I'm going to lose every single time, doesn't that mean I might win? In fact, doesn't that mean I might win actually more than once? Ooh, yeah. So we're going to analyze this. This kind of defies common sense at first. Every time I play, I'm probably going to lose. There's no question. And there's no such thing as, oh, I am due. I have people say things like that. Oh, the luck has got to change. I've got to. No, you don't. It's like saying, I'm going to flip a coin that landed tails. Well, the next one's got to land heads. No, it doesn't. It might land tails again. The slot machine isn't keeping track for you. But I just did the same thing over and over and over and over and over again. I can calculate the probability. So let me ask you a question. You're going to play 1,000 times. Okay, probability of losing 1,000 times. What is the complement of losing every single time you play? What's the complement of that? It's not winning every time you play. No, I'm playing 1,000 times. Think of it this way. Could I win? You know, I'm playing 1,000 times. Is it possible for me to win 1,000? Yes, not likely. How about 999? Yeah. 998? Yeah. You know, down to 3, 2, 1. Losing every time means I won 0 times. So if I play the slot machine 1,000 times, I can win 0 times, or I can win 1 time, or I can win 2 times, all the way up to 1,000. Does that make sense? I lost every single time. What is the complement of losing every single time in words? Winning
Probability
at least
0 times.
Well, no, at least
Once.
Losing every time. What's the only thing else? Winning at least once. Does that make sense? Oh, winning at least once means 1 or 2 or 3, all the way up to 1,000. Losing every time means I won exactly 0 times.
Yeah.
So does this make sense to you? The complement of losing every time is winning at least once. By the way, this would be true in every scenario.
Makes sense.
That'd be kind of like saying, well, what's the complement of me failing every time? Not failing at least once. Okay.
Just don't end up like that person who spent his entire life savings on carnival games.
We're not going to get into the mathematics of gambling, but this one might actually surprise you. So I'm going to change the question now to find the probability of winning at least once. Now, at least once means 1 or 2 or 3 or 4. I'm not going to calculate all of those. I just want to know what's the probability that I win at least once, because at least once is the complement of not at all. Anybody want to guess how I find the answer? It's going to be 1 minus this. So if I do that on my calculator, it's 1 minus this. So I'll just do that on my calculator. And that's approximately 0.8649. These have to add up to 1, by the way. Now, this is the part that really throws a monkey wrench into your reasoning. Okay. I want to play a slot machine one time. I'm probably going to lose. I'm going to play it again. I'm probably going to lose. I'm going to play it again. I'm probably going to lose. I've already decided I'm going to play it 1,000 times. The probability of me losing all 1,000 times is actually really low. The probability that I win at least once is actually really, really high. Does that guarantee you're going to win, by the way? If the probability is this, does that guarantee you're going to win?
No.
No, but it means you probably will. I'm going to use basketball as an analogy. If this is your free throw percentage, you make 86% of your free throws. You're a good free throw shooter. You're going to the line to shoot a free throw. Are you going to make it if you make this percentage of your free throws, that probability? Are you going to make it? I think the answer would be probably, because you make the vast majority. But just because you make it most of the time, does it guarantee you're going to make the next one? No. You might miss, but the probability that you make it is really, really high. Is everybody following me on that one? I have got a field goal kicker in a football game. He has a great percentage. So does that guarantee he's going to make the field goal? No, it means he's probably going to make it. Right? Your team is a huge favorite over the other team. Are they going to win the game? They probably will, but they still might lose. There's no guarantee unless the probability is 1. But here's the point. You just played a game 1,000 times where you're probably going to lose every time. But if you played it 1,000 times, the probability you win at least once is actually really, really high. So does that mean you should all go to the casino and play 1,000 times? No, because here's the thing. Even if you do win, the amount you win won't be as much as you lost. You're still going to, it doesn't work that way. You're not going to get all of it back if you win. You're going to get some money back. They do that way on purpose. So in the long run, even though you're going to win eventually, right? In fact, if I play 1,000 times, remember we said the probability of you winning was 0.002. That's 2 out of 1,000. So common sense. If the probability that I win is exactly 2 out of 1,000 and I play 1,000 times, isn't it reasonable that I ought to win a couple of times? Think about that logically. If the probability of winning is exactly 2 1,000ths and I play 1,000 times, then isn't it reasonable to say I probably should win a couple of times? What do you think? Yes? No?
Twice would be safe.
That would be, yeah, in fact, it's the most likely outcome. It doesn't mean you will. If I roll a single die, I have the numbers 1 through 6. If I roll a single die, you don't know what's going to happen next. But if all the numbers 1 through 6 are equally likely, then shouldn't I get the number 1 about 1/6 of the time? Shouldn't I get the number 2 about 1/6 of the time? You'd say, yeah, that makes sense. So I should win about 2 times out of every 1,000. So that's why this probability is so high. So this is called the mathematics of at least once. It actually has a name, the math of at least once. So I'm going to tell you a story. This is a true story. And I like to use this in my statistics classes. Okay, I used to love scary movies, but it's hard to find scary movies anymore. They're just rehashes. But I saw a scary movie. Now, it's probably been 20 years since a scary movie came out. And this movie is called Super Size Me. Has anybody ever heard of this?
I watched that in health class my senior year of high school, and I was so disgusted.
It's a documentary, and to me, it was the scariest movie I've ever seen. It's a documentary. It's actually true. Super Size Me is about a man who wanted to prove how bad fast food was for you, and the fast food industry was at its all-time thriving high. I believe the guy's name is Michael Moore. I think that's his name. It's been a long time since I've seen this. So what he did was, I don't want to mention because the lawsuit. So he went to a certain restaurant every day for like a month or two, in a certain restaurant, and that restaurant had the policy that they would randomly select customers when you walked up and they'd say, "Do you want to supersize your meal?" And I guess that meant everything was way bigger. And they didn't ask every customer. The company's official policy was that they were going to ask 1 out of every 5 customers. And literally the person at the cash register had a clicker. And every 5th customer, they'd say, do you want to supersize your meal? So this person went to McDonald's, the McRestaurant, don't want to name names, every single day for at least a month. And if they asked him, he'd supersize. Well, it turns out he ended up supersizing his meal way more often than that. And what he did was he kept track of the health benefits. And as his health started to, and he was a young, fit guy, as his health started to get worse over time, and all of the horrible things that happen on a fast food diet, and he was documenting this and going to doctors. Then what he also did was he kept track of, this is the scariest part, schools across the country. And that's probably, Destiny, what you were watching. It's schools, cafeterias across the country. What they were serving kids, it was unbelievable. I mean, literally, you know, like chicken nuggets and French fries kind of meal, you know, every day, deep fried fast food kind of meals at schools. And in a lot of cases, there was nothing in the diet that was healthy at all, especially in the lower income areas where the state may have been subsidizing it. So now they're literally feeding people just absolute garbage. And this went on for a long time. And they call this an expose. He exposed a lot of the really bad things that were happening and forced people to fix it. But what I'm saying when I talk about scary was that when you actually saw what was really going on in schools in terms of what they were feeding the kids, and some of you guys, you may be too young. In other words, they fixed it by the time you went to school. Or maybe you went to a school where you go, yeah, my cafeteria never actually gave real food. They, you know, old, frozen, deep fried, you know. But anyway, but the whole point of the supersize me that I like to use in statistics was, the whole point was he would go and he would automatically say yes every time they said, supersize me. And he wanted to show, because the company policy said was, no, we only do like 1 out of 5 because we don't want that, because we know the obesity and all the things that are affects. But he did this every day for a really long period of time. So if the company is only asking 1 in 5 people, then it makes sense that he should have only been asked about 1/5 of the time. But he was asked far more often than 1/5 of the time, which means that there's something not quite right. So here's what I want to do. You are going to a certain restaurant, and let's say we'll use the exact same numbers. We'll say the probability of being asked, and I think I have this one on a quiz too, by the way, to supersize. Let's say, let's just make up a number. Let's say the probability that you're going to be asked to supersize, hang on one second, I want to make sure, I don't want to use the same numbers exactly. Okay, let's say the probability of being asked to supersize is exactly 1/5. They ask you they really do ask 1/5 of every customer, and they literally count every 5th customer we're going to ask. So you are going to go to this particular place, okay? You make 10 visits. Yeah, you like this particular place. You're going to visit this restaurant 10 times. Now, if they ask 1/5 of the people, don't you think you should be asked at least a couple of times? That seems reasonable, okay? You're going to go 10 times. I want to find the probability of being asked, and again, the key is at least once. I'm going to walk you through this process. I'm not asking you what's the probability of being asked exactly this many times. I'm saying, no, what's the probability that you're going to be asked at least once? Okay. You're going to the particular restaurant. They ask exactly 1 out of every 5 people. So you don't know if you're going to be asked ever. So you go through 10 times. So how do I do this calculation? Actually, there's 2 parts to the calculation. The first part is, let's find the probability that you are never asked. Okay, that's the easier calculation. So the probability of never being asked. Well, if the probability of being asked is 1/5, which by the way, it's totally okay if you want to convert that to a decimal. You could leave it as a fraction, it won't change anything. If the probability of being asked is 1/5 or 0.2, what's the probability that each time you go, you are not asked? Anybody? This is the probability of being asked. What's the probability of not being asked?
4/5.
Exactly, 4, 5, or 0.8. For the calculator purposes, it might be easier to use the 0.8. Just easier number to enter. So if the probability that you're going to be asked is 0.2, then the probability you're not asked, which is the only other outcome, has got to be 0.8. That's the complement. Remember, those two numbers have to add up to 1. So the probability of not being asked is 0.8. I would like to know the probability that you're not asked 10 times in a row. You go up, you're not asked, 0.8. Again, you go, you're not asked, 0.8, 0.8, 0.8, 0.8. So like the last example, shouldn't I be multiplying 0.8 by itself 10 times? What do you think? In 10 visits, you're never asked. So what is that probability? Anybody want to tell me? Using those numbers, 10 visits, you're never asked. What's that probability? Don't give me the calculation. Tell me what I'm going to enter into my calculator. The probability you're never asked. This is the probability of being asked. This is the probability of not being asked. And I'm not going to be asked 10 times in a row.
So it would be 0.8 to the power of 10.
Perfect. 0.8 to the power of 10. That's it. This is the probability that I'm never asked. Okay. Now, I don't know what that is. Let's calculate it. So 0.8 raised to the 10th power is approximately 0.1074 if I round it. That's not a very big number, is it? In other words, it's not very likely then if I go 10 times that I'm never going to be asked. That's a really small number. So now the question is, I wanted to know what is the probability now that I'm asked at least once? Let's write that down. At least once. This makes life good because at least once is the complement of none at all. I'm never asked. The complement is I'm asked at least once. Remember, in 10 visits, I could be asked 0 or 1 or 2 or 3 all the way up to 10. You just told me the probability of being asked 0 times. The complement would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or at least once. So the at least once should therefore be 1 minus this value, which would therefore be what, 0.8926 by just doing the arithmetic. Whoa. So although the company is only going to ask 1/5 of the customers if they want to do this, you go 10 times. The probability you're asked at least once is really, really high because you keep going. So although the probability of one occurrence isn't very big, you're doing it over and over and over and over again, it kind of stockpiles. Okay. So the probability of at least once, it's kind of a cool thing because what we always do is we calculate the probability of none, then take that value and subtract it from the number 1. And that will always give us the probability of at least once. So I'll write it down. It's not a formula as much as a technique, but let's write it down in simple terms. Now, here's the only thing. You have to know the probability of something happening. And that probability doesn't change. Like the slot machine, it doesn't change. The coin flip, it doesn't change. The roll of the dice. If the probability of whatever I'm looking at is the same every time, that's the key. The probability is not changing. If the probability is the same every time, then this calculation is fairly simple. So the probability of, I'll write in the words, at least once. This probability is equal to 1 minus the probability of, well, say none. The probability something does not occur means kind of like saying I failed every single time. If the probability of me passing a test is really small and I take a whole bunch of tests, I might fail every one of them. but eventually I might pass one. Because when we do this calculation, sometimes it's actually not, it's a lot bigger than we thought. The probability of at least once is 1 minus the probability of none, because the probability of none is the complement of at least once. So regardless of what it is you're doing, if you're counting the occurrences. Now, it could be something simple as this. You have a basketball in your hand and you're shooting free throws. And you're going to shoot a bunch of free throws. You already know ahead of time. I'm going to shoot 100 free throws. The probability that I miss every one of them, right? I can calculate that. The probability I make at least one is 1 minus that number. As long as I know the probability of it making the free throw before I start, that's the key. Now, one of my favorite examples of this. Okay. We talk about one of the rarest events that can possibly occur in a human being's life is getting struck by lightning. Do you all agree with that one? We hear that as being like one of the rarest occurrences. It turns out it's not exactly what you think. I used this problem in another class. I looked up the statistics, and it turns out the probability of being struck by lightning in your lifetime, it might surprise you. We weren't taking into account, by the way, where you live. You see, if you never go outside, maybe it's not that good. But the probability of being struck by lightning. Okay, make sure you're muted, guys. Make sure you're muted.
It's better if it's small, and so in pituitary fatigue.
We get that loud there. The probability of being struck by lightning in your lifetime. That's key. I don't mean today. Believe it or not, it's about 1 out of 15,000. 1 out of 15,000. There's 340 million Americans.
Maybe it depends on location.
Yeah, it would make sense. There's about 340 million Americans. That means that realistically, well over 20 of all the people right now in America that are alive right now in America, over 20,000 of them will be struck by lightning in their lifetime. That's a crazy statistic. 1 in 15,000. Okay, so here's my point. The probability of struck by lightning. Now, does that mean you individually are going to be struck by lightning? Now, you're far more likely to win that at that slot machine, aren't you? But here's what happens. Okay, I was at, and I can prove it, I have pictures on my phone. I was at the Raider Charger game on January 9th. It was awesome. That was my birthday present from my wife. There's 60,000 people at the stadium. Okay. My question to you is, what's the probability of at least one of these people being struck by lightning in their lifetime? There's 60,000 people at the stadium. What is the probability that at least one of these people is struck by lightning in their lifetime? Now, I have no idea what the number is. We have to put it on a calculator. But do you think it is very likely, or do you think it is very unlikely that one of these people, at least one of these people, will be struck by lightning in their lifetime? Anybody want to try on? If the probability of being struck by lightning is 1 in 15,000, and I have 60,000 people, well, 60,000 divided by 15,000 is 4. So it says, I think a few people are probably going to be struck by lightning at some point in their lifetime. I just like to know the probability that at least one of these 60,000 people, by the way, that includes me and my sons, we were all at the game. What is the probability that at some point, now, someone said location. Yeah, I think where you are in the United States might matter, because do we get a lot of lightning here in San Diego? No, but we do get lightning. Some of the greatest lightning storms earlier during this football season. We're sitting outside watching. It was cool. So there are places in the country that are more likely, some that are less likely, but we do get lightning in San Diego. So we're probably right in the middle. So how do I answer this question? Well, what's the probability that you're not struck by lightning? Okay. If 1 out of 15,000 is the probability that you are struck by lightning, what is the probability that you are not? I'll just put probability of not. Anybody? You're either struck by lightning or you're not. That's the probability that you are. What would be the probability that you're not struck by lightning in your lifetime? And I'm hoping you're in this group.
14,999 out of 15,000.
Perfect, because these have to add up to 1. You're exactly right. Now, what's the probability of at least 1? Let's start with the probability that nobody in this stadium is ever struck by lightning. So I'm not struck by lightning. My oldest son is not struck by lightning, so we'd multiply that. Then my youngest son not struck, we'd multiply that. Then the guy sitting next to me, multiply that. Then the lady sitting behind me, we'd multiply that. We'd do it 60,000 times. That means that's my exponent. You're not doing this by hand, that's why you have a calculator. So the probability that nobody is struck by lightning, do you agree that it's this number, 14,999 over 15,000, raised to the 60,000? Everybody cool with that? Now, you have a calculator. This is easy for your calculator. Difficult to do by hand, but easy to do on a calculator. So let's take 14,999 and divide it by 15,000. Do that first. Get a total. Now raise that value to the 60,000. And tell me what that number is. Tell me when you get a number. This is the probability that nobody in the stadium is ever struck by lightning in their lifetimes. So just holler out when you got a number. It can't take that long to do.
0.0183.
Yeah, 0.0183. Would you say that's pretty small? That's pretty small. That's less than 2%. The probability in this stadium that no one is ever struck by lightning is that. So what's the probability that at least one person in their lifetime, not again, we're not talking about today, we're just saying in their lifetime, the probability at least one person, well, I have to take 1 and subtract this number according to my formula, and I'm going to rewrite it like this: 14,999 over 15, 1, 2, 3, raised to the 60,000th power. But I have a calculator. That's not a difficult calculation. That should be 1 minus this number, or 0.9817. Does that kind of surprise you? A stadium of 60,000 people, the probability that at least one of the folks in the stadium is struck by lightning in their lifetime, 0.9, over 98% likely that at least one person. Yikes. So when it rains next time, all of us have to be a little bit careful, right? Next time there's a storm, because that's not equal to 1, but boy, that's really close to 1. That means it's close to certainty that at least one person is going to be struck by lightning in their lifetime. Now, I don't want you to walk around, being afraid of being struck by lightning, but obviously stay away from large stadiums. If there's a thunder or lightning storm, I don't know. But this is the mathematics of at least one. It involves complements. And that's one of the reasons that complements are so powerful, is that I can do these ridiculous calculations really, really fast. I just need a cheap calculator. Again, the key is the probability of whatever it is you're measuring, that probability is not changing. It's staying the same. Again, the dice roll, the coin flip, the cards, the slot machine, even the lightning. I have a probability, it's unchanging. Now, if I say, what's the probability, if I do the same thing over and over and over and over again, what's the probability of it never occurring? Then at least once is the complement of that. So that's why I'm doing this always in 2 stages: the probability of none, the probability of at least one. You notice we never actually used this number in a calculation, did we? Because this is the probability that it happened. This is the probability that it didn't happen. So that's the one that I end up using because I'm doing complements. Okay, so we are now finished. Let me stop.